Okay, folks, we last left, we were talking about this business about, finitely generated, well, we talked about finite abelian groups. So let me give you kind of this big theorem, which is basically what we've been talking about, with just a little tiny bit tacked on to it. This is the fundamental theorem of finitely generated abelian groups. If we have a finitely generated abelian group, finitely generated. What we've been talking about is finite abelian groups. If it's finitely generated, so it's only needs finitely many generators, then it's either finite or it's just a little bit more. G is isomorphical. The direct sum of some number of copies of we'll call this K equals 1 to N C, direct sum F, where F is finite. And the direct sum so either it's finite, so that's one kind of finite generated abelian group, or if it's not finite, it consists just of finitely many copies of Z. That's kind of cool. So any finitely generated abelian group is some number of copies of Z, direct sum of finite piece. And there don't even need to be any pieces here. F is called the torsion part of G. And so if you ever hear that terminology, that's what is being discussed. N is the rank of the torsion. So N is just the number of copies of Z that appear, if any, and if not, we can say 0. Okay, now I promised, and I am going to deliver on this last time, that we're going to get our hands dirty and do some computations to kind of show how this works. Let me give you one example. Here's one problem that we can solve for ourselves now. Example. Find up to isomorphism all abelian groups of order 2,250. By the way, if I asked you to find all groups of order 2,250 without the abelian adjective, you all should get the pitchforks and the torches and, you know, come storm the castle. That's a hard problem. It's doable, but it's very hard. The abelian part makes this a lot easier. The first thing I'm going to do is I'm going to factor this down into prime powers. So 2250, this is 10 times 225 squared, which is 10 times 15 squared. So it looks like the primes that divide this are like 2, 3, and 5, right? So there's 1, 2, 5. There's 1 here and 2 more here. and 2 3s here. What it looks like to me. It's 250 times 9. Yeah, that's right. Everybody okay with that? Now, in fact, I'm gonna give you all groups in terms of their invariant factors and elementary divisors. Elementary divisors in this case are prototypes. Okay. How many groups of order 2 are there? I know there's only one, right? So for 2, I have only Z2. Right, okay. For the prime 3, well, you've got your CLO subgroup, if you will, has order 9, right? So how many ways are there to break? How many groups of order 9 are there? Ask yourself, how many ways can you partition 2? One of them is this way. And another is this way. Think of this as the number of ways to factor 9 into powers of 3. 9 is 9 times 1, or it's 3 times 3. How about 5? Well, one group of 125 could be cyclic of order this. I could also break 125 down as 25 times 5. And one way to do this. Everybody agree that I've exhausted all the possibilities for breaking down. So think of it this way. This last one, Z125, that's 5 cubed. How many ways can you break down 3? Right, which is the exponent. 3, or it's 2 plus 1, or it's 1 plus 1 plus 1. And that's essentially what we've done here. Same here with 3 squared. It's either 2 or 1 plus 1. Everybody okay with that? Everybody clear on this? So basically what the theorem says is, here's what I know. The CLO 2 group, that's it. It's Z2, end of story. The CLO 3 group, it's one of these 2 animals, right? So I got 2 choices now. Right? The CLO 5 group is 3 choices. How many different groups for 2250 are there? 6, right? Because I'm making 3 choices. The CLO 2 group, I'm forced. There's only one way to do that. The CLO 3 group, there's 2 ways to do that. And the CLO 5, there's 3 ways to do that. 1 times 2 times 3 is 6. Let me list what these groups are. And I'm going to use this to do the invariant factor decomposition. So there should be 6 possibilities. And I'll just go through them. I think I'll start from the bottom. 1, C125, direct sum, C9, direct sum, Z2. Or I could go C125, direct sum, C3 sum, C3, direct sum, C2. Here I've basically buried my CLO 3 group. Now I've exhausted all the possibilities for Z125, so let's go next to 25, direct sum C5, Z9, C2, and and vary that below 3 group again. And finally, I have the case where the CELO 5 group is this. And C5, it's C5. These are all different. And if I walk up to you on the street and I tell you, so you were asking about isomorphism earlier, what does it mean up to isomorphism? If I walk up to you on the street and I give you a group that is of that order and it's abelian, I promise you it has to be isomorphic to one in the list of these 6. All right. Everybody okay with it? These are all the possible elementary divisor decompositions for a group of order 2,250. I will also, in tandem, give the invariant factor decomposition. You can work this both ways. I'll show you how to work from elementary divisor to invariant factor. By the way, let me ask you all this. One group that I know of order 2,250 is the group that is cyclic of order 2,250. That should be one of them in the list. Which one of the 6 is it? Anybody know? Which one of these 6? One of these 6 should be cyclic of order 2,250. Which one is it? It's the first one. Why is that true? Y'all remember this thing that we talked about earlier? If A and B are relatively prime, then Z direct sum A, Z direct sum B is Z direct or Z sub AB, right? So 125, 9, and 2, they're all pairwise relatively prime. So this is Z, the product of these 3, which is 2250. Here's the way I do invariant factoring. Be greedy, right? Do the same trick here. 125 is the highest power of 5 that I see here. 3 is the highest power here, and 2 is here. So 125 times 3 times 2 is, I guess it's going to be 750. And I used up everything except the straggler Z3. I put this in the opposite order of the usual invariant factor decomposition, but notice these 2 are cyclic and 3 divides 750 and their product is 2250. What is the invariant factor decomposition here? Biggest power of 5 I see is 25 times 9 times 2 is 450. I've got the straggler Z5 left over. 5 divides 450 and their product is 2250. What is it here? Go through biggest power of 5, 25 times 3 times 2. That's going to be, I guess it's going to be 150, isn't it? And then go through, so we've used up these. Now go through what's left. I get the C50. How about this one? Well, let's see. 5 times 9 is 45 times 2 is 90. What's left over is 5. And there's another 5. That. So this one has 3 cyclic factors. Notice 5 divides 5, 5 divides 90, and their product is 2250. Yes.
Why were you allowed to combine into a Z15, but you can't combine these two Z5s?
Because 3 and 5 are relatively prime and 5 and 5 aren't. Yes.
Oh, for the homework, did you want us to do?
I don't remember. Whatever I asked you, whatever the instructions are. If I said, did I say find all groups of that of order 15,000?
Yes, find out.
Then I don't care. It's a good exercise for you if you check and do
Okay.
it both directions, but all I really care is you do one of them. I would, if I were you, make it clear to the grader, I am doing invariant factor, I am doing elementary divisor, or do both. How about this one? 5 times 3 is 2 is 30. 5, 3, 15. And 5. And there you go. Everybody see how to do that? Well, let's check it out. Okay, so, all right, so here's the moral of this story. If I have a group of order 2,250 and it's abelian, it has to be in one of these forms. These are the elementary divisor decompositions you might encounter. These are the invariant factors, and we've translated. By the way, of course, you can always translate back and forth as well. You might think, how do you go from, if I start with invariant factor to elementary divisor? By the way, can somebody give me an example of when it might occur that the elementary divisor and the invariant factor give you the same answer, right? So what I mean is, notice that the sort of the presentations look different, right? I wrote Z2250, and this looks different from this looks different from this, and so forth. When might it be the case when I do the elementary divisor decompositions, then I get exactly the same thing over on the right column? Anybody think? Yes.
Is it all the primes are to the first power? That makes sense. It's a product of the order, obviously it's a product of prime.
But here all the primes are to the first power, right here, and it looks different over here.
Like if we factor, like you said, order 2250, if the order when we factor it, we get a product of primes that are all to the first power. That's what I mean. Is that still wrong?
Yeah, go the other direction.
Okay.
If when you factor it, it's a single prime to a power, then you will get the same thing, right? So that's one, so you might think about it and see if it's an if and only if. If you have a single prime to a power, then the invariant factors in the elementary divisor should look the same. Okay, let's do another example here. Find variant factor and elementary divisor. Decomposition for following group. I've got $50 that says I'm gonna regret this, but we'll do it. The first thing I'm gonna do. This is by the way, this is a very large group, right? And the number of elements in this group, 72 times 18 times 24, 147 times 100 times 80 times 25 times 16. A very large group. Now, suppose I want to get the elementary divisor and the invariant factor. The first step that I'm gonna do is I'm gonna take each one of these numbers that I see here, and I'm gonna bust it up into prime powers, right? So G is isomorphic to eight times 9 is 72, right? And since 8 and 9 are the different prime powers dividing 72, this works. Everybody okay with that? This is the Z72. 18, Z2, direct sum, Z9. Everybody with me on that? 24, that's 8 times 3. Uh, 147, that's 3 times 49. $100, that's 4 times 25. 80, that is 16 times 5. $25, that's 25. 16, that's 16. So those last two were more convenient. They were already prime powers. Everybody okay with that? Yes.
Why are we leaving 25, or why are we leaving 25 and 16 by themselves again?
Because they're prime powers already.
Upward.
Everybody okay with that? Everybody see what we did so far? Yeah, I want you guys to make sure you understand this because you know it's going to show up on the next test and it is bread and butter, baby. So make sure you know how to do this. Okay, the first thing I like to do is I like to break this up into a CELO subgroups, right? What primes are in play here? Well, 2, 3, 7, 5, and that's it. 2, 3, 5, 7 are the primes in play. So I'm going to do the CELO 2 group first. And I'm just going to go through, I'm going to write this in descending prime powers that I see. Let's see, there's an 8, a 2, an 8, a 4, a 16, and another 16. So I see 2 16s. Those are the biggest powers for 2 I see. Okay, I got those covered. I've got an 8. And how many of those do I have? Looks like I got 2 of them. C8, C8. Do I got any 4s? I got 1 4. And looks like, surprisingly, I've only got 1 2. Okay. Actually, this is the CELO 2 subgroup. It's just this direct sum of 2 Z16s, 2 Z8s, a Z4 and a Z2. Everybody with me so far? Everybody good so far? Okay, let's look at 3. What's the biggest power of 3 I see? There's a couple of 9s, a couple of 3s. Okay, it looks like I got 2 9s. There you go. And looks like I've got a 3, 3, and that's it. Okay. And I forgot to check that Z2, didn't I? It was just one there. Okay. Okay, the next prime I come to is 5. Let's see. This It's all gone. There's a 25 and a 25, so there's two of these. And then 1, 5. And finally, it looks like the last thing I've got is Z49. There are 4 different primes that divide this group, or the order of this group, I should say. 2, and this is CeeLo 2 group, this is CeeLo 3 group, this is CeeLo 5 group, CeeLo 7 group. Okay, any questions? Yes.
I'm a little bit confused about why you chose to break it down initially the way you did.
Just because I wanted to group I wanted to, well, actually what I have here at this point is I have the elementary divisor decomposition, as a matter of fact. This is because look at what I've got. For the prime 2, I have this decomposition like this, right? Here's the prime power subgroups. Notice every little piece here is a prime power, and that's what I wanted to get. That's essentially what the elementary divisor decomposition is. In fact, at this point right here, it's an elementary divisor decomposition. It's just all scrambled up and a little disorganized. But if you look at what's going on here, these are all prime power order groups. So it's already in the elementary divisor decomposition. And all I did to go from here to here was just group it in a different order so it's more organized. My elementary divisors here are 16, 16, 8, 8, 4, 2. And then corresponding to 3, the elementary divisors here, 9, 9, 3, 3. Then 25, 25, 5, finally 49.
Like, how would we know not to break Z100 into like 5 and 20?
Because those aren't relatively prime.
Okay.
Right? You break it up into prime powers, right? And 100, although it is 5 times 20, 5 and 20 share that factor of 5. So I wanted 4 times 25, right? And that's the only way to do it, is to break it up into prime power. Actually, the fact that integers factor uniquely into primes, more generally into prime powers, then that's very useful here. Right? Is everybody okay with that? This is actually elementary divisor here. This is organized elementary divisor. Everybody okay with this? Okay, so now we go on. Let's get the invariant factor. And I'm going to do a greedy algorithm here to get the invariant factor. Okay, here's what I'm going to do. I'm going to be greedy and I'm going to pick off biggest. That's why I organize them this way. The first, what's the biggest cyclic piece that I can use? 16 times 9 times 25 times 49. So that's going to be 441 times 400. Right. Yep. Looks like this first one is Z, and if you like, you could certainly write this as Z 16 times 9 times 25 times 49. That's okay as well. let's pick out the second one. 16 times 9 times 25. So it's the same as before, except it's missing that 49. Yes.
How are you able to, when you say you're to pick out like the cyclic group, how are you able to do like the 16, 9, 25, and 49 and like know that that's? You're like,
Because it's the largest. That's why I arranged it this way.
okay,
Because whenever you have relatively prime things, like 16 times 9, this piece right here is cyclic
okay,
because those two numbers are relatively prime. So what I'm doing is I'm taking the biggest relatively prime chunks that I can, sticking them together. And that makes my biggest cyclic piece. Does that make sense?
yes.
So what do I got next? I've got 16 times 9, 25. So that's 400 times 9 is 3,600. Are you okay with that? Okay, next piece. 8 times 3 is 24. Times 5 is 100. Next piece. 8 times 3, 24. And now notice everything else comes out of the CeeLo 2 subgroup because I've used up all the other primes. So the next piece is Z4. And the last piece is Z2. And this is the same as this. This is just written in the elementary divisor, so it's written out kind of in the naked prime powers. And this one is arranged into cyclic pieces, right? Notice that this is in a certain sense kind of more economical, right? So you've got one big cyclic piece right here and the divisors of that coming off of here. The exponent of this group is whatever that is, 176,400. So the order of this group is very, very large. It's the product of these 1, 2, 3, 4, 5, 6 numbers. Very large number. However, the exponent of the group is 176,400, which means the order of every element in this group divides that, which is much smaller than actually the order of the group itself. Everybody see how to do this? If I walked up to you on the street and gave you this and gave you the invariant factor first, it's pretty easy to cook it backwards because what you do, well, I mean, assuming that you can factor this, right? You have to break out your calculator, break this down into prime powers, break this down into prime powers, this into prime power, this into prime powers, and so forth. And then it's the same as this step to here. You're just breaking things down. Okay. Any questions on that? Yes. Any questions? All right. So we are going to do just a little bit more about groups before we break into rings. And what we're going to talk about now in this final chapter is composition, series, and solvability. So in this section, I mostly want to equate you, well, so let me write this down first. Composition, series, and solvability. Let me tell you, just right out, the takeaway from this section is mostly definitions. I mostly want to acquaint you with the terminology and what these animals are. We're not going to do a lot of theorems, except for one. There's going to be one kind of crowning theorem at the end of this section called the Jordan I'm sorry, called the Jordan-Holder theorem, and that's gonna be kind of the big takeaway of this. But I want to acquaint you with what this is. It might be a little, well, we'll get our heads wrapped around this. One of the main reasons that I talk about this is in this section really is the motivation for studying the classification groups. This was actually one of the great problems mathematically in abstract algebra, in particular group theory, that lasted probably from the 50s until actually fairly recently. There was a lot of effort put into classifying, understanding what all finite simple groups look like. Remember what simple means. It means the only normal subgroups are itself and the identity. Well, if you want to look at the abelian simple groups, they're just Z mod P. And there you go, that's done. The ones that are not abelian are more difficult. They're more troublesome to classify. One large family is, for example, the alternating group A5. There are certain large families of matrix groups and things called group of Lie type and so forth. So there was this list that was put together of these infinite families of groups, like the alternating groups and these matrix groups and so forth. And it was proved these are simple. So now we've got these lists. There's also another 26 groups that do not fit into any of these infinite lists. They're called sporadic groups. And it took a long time to prove that there were, and seriously, the proof for something like this, at one point, somebody had proved that there could be no more than 30 sporadic groups, and they had a list of 24. And then somebody came up with the 25th, and they proved that there could be no more than 29. And it was a process that was similar to this, and it basically converged to a list of 26 sporadic groups. This proof of the classification of finite simple groups took well over 10,000 pages, scattered through hundreds of papers throughout the literature. It was a great mathematical achievement. Why? Because group theorists couldn't get a date on Saturday night? Is that why they did this? Well, partially. But the main reason was that simple groups are the building blocks of other groups. And in this section, we'll talk about how they're an important piece of the puzzle and why there was so much effort put into trying to figure out what these are. I'm going to start off with hopefully a familiar definition. If G is a group and XY is G, the commutator of X and Y is defined as X inverse Y inverse X, Y. Additionally, we denote by G prime or G1, the commutator subgroup of G1. Now, this is why this was in the homework earlier. We got to be a little careful here. The commutator subgroup is, don't think that this is just the group consisting of all commutators, because here's the problem. Commutators do not form a subgroup. So what the commutator subgroup is it is the smallest subgroup of G that contains all possible commutators. So in other words, This is the group generated by all commutators. So it's the smallest group that contains the set of all commutators. Now, if you remember back to your homework, hopefully, you actually proved a couple of things when we talked about commutators. Number one, you proved that the inverse of a commutator was a commutator, right? So in other words, if you have if you take the inverse of a commutator, this is the inverse of this thing. Right? And we know in group theory, to get the inverse of this, you kind of do the inverse of everybody in reverse. Do you recognize that as a commutator? That should be what? Okay, so what this line says is it's speaking to me, and it's saying the inverse of the commutator xy is this other commutator, yx. Everybody agree with that? You also proved in that homework that if you have a conjugate of a commutator, it's still a commutator, right? So if you have g xy, g inverse, this is g x inverse, y inverse, x, y, g inverse. Agreed? Now, let me use my usual flair for the dramatic. G x inverse, y inverse, x, y, g. Now, see what I can do with this. G inverse, G, G inverse, G, G inverse, oh, no wonder. Which way did I do this? That should be an inverse there. There we go. So hopefully y'all see what I did. I just kind of shoved a G inverse G in between the cracks here. Now I'll arrange it that way. And this first one notice this first piece here is the inverse of this, right? Because if I invert this, I get G x inverse G inverse. And same here. So this is actually the commutator G x G inverse G y G inverse. So one of the things that we showed is commutators are closed under inverses and they're closed under conjugation. So I just said that the commutators by themselves don't form a subgroup. You have to look at the smallest group that contains the commutators. Why is that? Yes.
Sorry, I was wondering, you specified in, I think you're about to address it, but you specified in what you said, but not in writing. This specifically has to be the smallest commutator. How come all commutators is different?
Because all commutators might be a smaller set. If I just give you the set of commutators, it's not necessarily a group. Here's the problem. It may not be closed under multiplication, right? Here's the real problem with commutators. If I have x, y times w, z, Well, what the heck is this? Well, this is X inverse, Y inverse, XY, then W inverse, Z inverse, WZ. Is it clear that you can write this as A inverse, B inverse, AB? It's not clear how to do that at all. And do you know why it's not clear how you can do that? Because it ain't always true. That's the problem. Sometimes, yes, you can do some kind of algebraic prestidigitation to be able to rewrite a product of two commutators as a single, but not in general. Not in general. And that's why we need the group generated by. Yes.
Would this be a normal subgroup?
The commutator subgroup is always normal. That is correct. It is always normal.
Because it's closed under conjugation.
That's right. And so when you take a product of commutators, it's just a similar thing to this. The product of commutators is closed under conjugation as well. And so that takes care of it. Because actually, you've got inverses, you've got associativity because it's a subset of an associative group. The identity is the commutator because it's the identity EE commutator, right? The only thing you don't have is closed under products, and that's why we have the definition. So instead of saying the commutator subgroup, instead a typical element in the commutator subgroup, instead of being a single commutator, it's just a bunch of commutators strung together. That's basically it. Okay, so this is kind of a old crash course. Remembrance of an old friend. This is the commutator subgroup. Let me give you a theorem that concerns us. Some of this stuff you've already done in the homework, and some of it is maybe a little bit new. So theorem 812. Let's let G be a group and X, Y, and G. And H is subgroup of G. Number one, X, Y. So the two elements X and Y commute if and only if the commutator X, Y is one. You all proved that many moons ago in the homework. H is normal in G if and only if, you didn't prove this, but this is pretty easy to show. If and only if let me tell you what this means. This is generated by commutators, this form. So when I see this is a set commutator, this means that this is generated by commutators where the lead is in H and the other is in G. Oh, wait a minute. That's normal in G if and only if this is contained in H. Yes. You might see if you can show that. It's not too difficult actually, but it's a good exercise. If F from G to H is a homomorphism, well, let me say G to G. That's G to K is a homomorphism. Then F of a commutator is the commutator Fx of Y. So in particular, G is a characteristic subgroup. The commutator is characteristic G, and so in particular, G prime is normal in G. That's another route. You actually showed the commutator is normal in your homework. So G mod G is the largest abelian quotient. Or G mod G prime is largest abelian quotient. And I will make that precise. That is G mod G prime is abelian. Well, and if N is normal in G and G mod N is abelian, then G prime is contained in F. Okay, some of the stuff you might think about for anything that you're not sure about, and we'll pick it up there next time. Any questions? Questions? All right, y'all have a good one, and we will see you on Wednesday.